All right, today we're just going to do a really quick review of all the stuff you should already know and have been doing for a year already. For example, different methods of charging something. When I say charging something, I don't mean plugging your iPad into the wall and charging it. That's not really charging, at least not the kind of charging that we're talking about. Kinds of charging we're talking about is the kind that you wear a pair of wool socks, rub your feet on the carpet, and then shock your little brother or sister. That's the kind of charging we're interested in. Of course, that involves actually gaining or losing electrons to give yourself a negative or a positive charge. Does that make sense? All right, so 3 kinds of charging. Friction, that's how you charge a balloon, by rubbing it up against your head. Conduction or contact, that's once you've done that, you can use that balloon to charge somebody else. And then induction, do you guys know what induction is? Charging by induction? Where you take a balloon, rub it on your head to make it negative. Then you take that balloon. I really wish I had some aluminum foil in here, I'd show you. So I'm going to take this balloon, rub it against my head to charge it by friction. Now we all met Herbin, right? Did everybody meet Herbin? Herbin, head red balloon is negative. Take this balloon, bring it close to the aluminum foil. Okay, so what do the electrons in the aluminum foil do?
They get pushed away from.
They move away from the balloon. They go over to the other side. So if, I don't know, say 10 electrons move from here to there, that means we got 10 electrons over on the far side. What's on the near side?
10 protons.
Yeah, 10 unelectroned protons. Meaning, over on the far side, you've got a charge of negative 10 electrons worth, and on the near side, you've got a charge of positive 10 electrons worth. Well, wait, no. Negative 10 elementary charges and positive 10. Okay, fine, whatever. Okay, so I'm going to leave this balloon here, and I'm going to very carefully, actually, could you hold the balloon so it doesn't move? Okay. Now I'm going to very carefully, I've got a negative side and a positive side, right? Very carefully rip the aluminum foil in half. Now what do I have? I have 2 pieces. What's this one?
Negative.
Negative. What's this one?
Positive.
Positive. Got it? All right, that's called charging by induction and separation.
Glad we had such good aluminum foil to
Right.
demonstrate this process.
All right, so next one. For those of you who are listening on YouTube, I came unprepared, and my aluminum foil sounds a lot like paper.
Because it is.
Shh. All right, next one. So we have yet another piece of uncharged aluminum foil that we're going to rub on our head. My head, not our heads. That's creepy. All right, and we're going to take this and bring it close. Now, again, what happened to the electrons?
Got pushed away.
They moved away from the balloon. So we got a negative side and a positive side. But this time, instead of ripping the aluminum foil in half, I'm going to touch the negative end of the aluminum foil with my finger. Doink. What just happened?
Well, the electrons
Transfer to your finger.
Electrons go into me, which means that now, if they all did, that means that this end of the aluminum foil is neutral. What's this end of the aluminum foil?
Positive.
Positive. So now I've got a neutral end and a positive end. If I take the balloon away, what's the charge on the foil? Positive. So I started with a negatively charged balloon and ended with a positively charged piece of metal. Got it? And I did that because I grounded one side. That's called induction and grounding. So, yes, induction means to induce a charge separation. And you can do that with a conductor because charges flow freely in a conductor and can go all the way to the other side. But if, I don't know, if I did the same experiment with paper, say, would it work? If I brought the balloon close to a piece of paper, why wouldn't it work? Paper is an insulator. What difference does it make? Yeah, even though the electrons do get pushed that way, they don't actually move because they're tightly bound. And because they're tightly bound, they don't move. No matter what I do, it's not going to work. Make sense? Because the whole premise is that the electrons can move from one side to the other. Sound good? All right, so that's induction. All right. Now, different scenario. Let's say I had 4 imaginary metal balls floating in space in front of me. 1, 2, 3, 4. All right, can you all see the imaginary metal balls? Good. Now, they all start off uncharged, but I stick 8 coulombs of charge on this one. Got it? And it's floating here. It's 8, 0, 0, 0. Now, I take these 4 balls and go doink, doink, and then arrange them in a square pattern. And then I remove them from each other. How many charges are on each one? How much charge is on each one? 2 coulombs on each. Why?
Because when you put them together, then the 8 get shared by them when you separate them.
Yeah, let's say they were electrons, 8 big electrons. Well, we all know that the reason everything happens in chemistry is that electrons hate each other, right? And so what's the best way to deal with that? If you've got 4 corners,
Push them
2
away.
will go on each corner. Right. Okay, so that's pretty straightforward. Let's try a different scenario. You still have 4 neutral balls floating in front of your head. One of them you go doink and it now has a charge of 8 coulombs. All right, so here's what we do. We take the first ball and the second ball and tap them together, doink. And then we take the second and the third ball and go doink. And then we take the third and the fourth ball and go doink. What's the charge on each ball? Yes.
4, 2, 1, 1.
4, 2, 1, 1. Nicely done. Everybody get how that works? All right, last one. We get rid of 2 of the imaginary balls, so we have 2 left. On one of the imaginary metal balls, we put a charge of +2. On the other one, we put a charge of -1. What's the force between them if they're, I don't know, this far apart? Wouldn't it be -2 kqqq over d squared? -2, right? Because it's -2, or 2 times -1 is -2. Or another way to say that is 2 attractive. Good so far? Now, what if you took those 2 balls and went doink, so they touched together and then separated them again? What's the new force? Well, what's the new charge on each ball?
0 and 1.
No, not 0 and 1.
It goes 2 and -1. That was the original charges?
2 and -1 were the original.
One would be 1/2 on each.
1/2 on each. Because the charge has to equalize, right? So it's the average of the 2. Right, add up all the charges, divide by 2, you get 1/2. Okay, so what's the new force? 1/4 kqqq over d squared, right? So how does the new force compare to the original force?
It's repulsive versus attractive.
It's repulsive versus attractive, and what about the magnitude?
It's smaller.
By how much?
8.
1/8 the original force. Got it? All right, cool. Moving on. An electroscope. So the other class has all the electroscopes right now, so I don't have one to show you, but I do have one drawn up on the board. Raise your hand if you have ever used an electroscope before. One person. Okay. Raise your hand if you've heard of an electroscope. 4 people. Raise your hand if you haven't heard of an electroscope. All right, the remainder. Good. So, what an electroscope is it's just a metal device. It's got a big metal plate on top. Big metal plate on top. It's got a metal rod that comes down the middle, and then 2 hanging pieces of metal that are on hinges. All right, and those hanging metal strips can swing back and forth freely. All right, but normally they're hanging straight down. Now, what would happen if you brought a negatively charged object close to that metal plate. Well, what would happen to the electrons in all this metal?
They get pushed down.
They get pushed down into these hanging metal pieces. Well, if you've got this piece has electrons on it and this piece has electrons on it, what are they going to do? They're going to repel from each other. So this electroscope is a way to determine how much charge is present. Now, if you actually took that metal or that negatively charged rod and tapped it against your electroscope, guess what happens? Well, now you've actually put some negative charges, so you've neutralized the top part, and they're still pushed apart, right? Okay, so that's about all you really need to know about an electroscope. It's just a way to measure charge. Next up, Coulombs Law. I know you guys all started the homework already. Basic idea is KQQ over D squared. When you're doing a problem with KQQ over D squared, first of all, it's only for point charges. Second of all, forget about the negative signs when you're doing Q times Q. Just treat everything as positive. You know what I mean when I say that? Treat everything as positive to get a magnitude of a force, and then you get the direction of the force from the picture. So if you had a positive here and a positive here, what are they going to do? They're going to repel with a force of KQQ over D squared. And then you know if they're repelling, then this one has to go down and to the right, and this one has to go up and to the left. Sound good? All right. Likewise, electric field is KQ over D squared, and you're going to get the direction, based on the sum of away from positive and toward negative. All right. Next up, tricky spot. Let's say you had 3 charges, 3 positive charge, one A, B, and C. If you want to figure out the total field at this point P, it's the vector sum of the field from C plus the field from A plus the field from B, right? You need to set yourself up an XY table. And the confusing spot is this distance here is square root of 5. If this is 1, this is 2, then that's square root of 5 across the diagonal, right? Because it's square root of 1 plus 4. Yeah. So the x component of B is going to be KQ over square root of 5 squared times cosine, and the y component is KQ over square root of 5 squared times sine. All right? And you got to remember to put the square root of 5 squared times the cosine or times the sine. All right. Now, last one. I'm going to tell you a true story right now. This is a true story.
It's one of those true stories that are true stories until you make part of it up to make it relevant.
I have no idea what you're talking about. All right. So, after graduating from college, I'm a young college graduate, got my butt kicked in college, and I proceeded to go get my butt kicked in the Navy.
Wait, like literally or like a...
No, not figuratively, not literally. No, there was no actual
Kicking of butts.
kicking of butts.
Okay.
But I went to Navy Nuclear Power School, and then I went to Navy Prototype, where I learned to operate a prototype reactor. And the problem with being at Prototype is you're on working 12-hour shifts, and your schedule's changing every few days. So sometimes you're up during the day, 3 days later you're up during the night, 4 days after that you're up during the day again. It was awful. So, and I'm studying nonstop while I'm doing all this. And so I was working 12-hour days and working in a place there was no refrigerator and there's no cafeteria. So you had to bring whatever food you were going to eat for that 12-hour period. I'm a big fan of PBJ sandwiches. Love the peanut butter and jelly. And so this was easy for me. What I do when I got ready to go to work in the morning is I'd make 4 PBJ sandwiches. And what I do is I'd lay out the bread, like 8 slices like that. And I have the peanut butter jar here and the jelly jar here, and everything would be underneath, all the bread would be underneath aluminum foil. All right? And then what I do is I open out the peanut butter jar, take my knife and go, peanut butter, peanut butter, peanut butter, peanut butter, wipe it off, jelly, 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 right? And then I go, put the knife down, fold, 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 and then I take the aluminum and go fold, 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 and I'd have my stack of 4 peanut butter jelly sandwiches that I could unfurl as necessary whenever I got hungry. This is what I did every day. Now, as you can probably imagine, working 12 hours at a time, that didn't leave me a whole lot of time. So I wanted to get this done as efficiently as possible. And I thought to myself, what can I do to make this go faster? I mean, it's already pretty good, but I want to make it go faster. So I thought, well, why don't I make a peanut butter gun? Peanut butter gun. And so that's what I did. I made a peanut butter gun. The peanut butter gun looks like this. Looks suspiciously like a spray bottle. All right, so we're going to draw a peanut butter gun. Okay, so here's it's got the nozzle with the handle on it. And then on the side it's labeled PB for peanut butter. And then what do? You take the peanut butter gun, you line it up with your slice of bread, like that, and then you pull the trigger, and then you've got a peanut butter slice of bread. Make sense? And I was thinking, this is great. I can just go, and I got all of my peanut butter, and I could do the same thing for the jelly, and then fold it, and then it's even faster than using a knife, right? I'm thinking to myself, I'm pretty smart for coming up with this.
Wasn't it hard to clean?
Oh, it's a piece of cake. Piece of cake, yeah. You just pour more peanut butter in it. So I'm thinking to myself, well, this is pretty good. But I think I could do one better than the basic peanut butter gun. What if I used my peanut butter gun, instead of doing 1 sandwich at a time, I can actually do all 4 sandwiches at a time? All right, how do you do that? Well, yeah, so what you do is you set it up so you've got the 4 sandwiches, right, like that. Slice, 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 in a 2x2 grid. And then you just arrange them in this 2x2 grid, and then you go back a certain distance, and you go once, and you get, instead of getting 1 of them, you get all 4 of them. Like that. Now, isn't that better?
But it's a smaller amount of peanut butter on each piece of bread.
Ah, the fundamental flaw in the thinking. When I pull the trigger once, assuming that 1 trigger pull gives me enough peanut butter per slice, what happens to the intensity of the peanut butter?
It decreases
By how much?
4 times. It's 1/4 as much as it was before.
It's 1/4 of the amount of peanut butter per slice. Wouldn't you agree? Now, so the idea is, if I go 4 times the area, it's going to be 1/4 the intensity. Wouldn't you agree? Now, how far away would I have to hold the peanut butter gun in order to hit all 4 slices, as compared to just the 1 slice? Twice as far away. What if I wanted to do the same trick with 9 slices?
3 times as far away.
3 times as far away. What about 16 slices?
4 times as far away.
4 times as far away. You see how this is going? So the peanut butter is spreading horizontally and it's spreading vertically. It's spreading in 2 dimensions as you go further and further out. Spreading in 2 dimensions. So if you quintuple the distance, how many slices is it going to be?
25.
25. What's the intensity going to be?
1/25.
1/25 the intensity of the peanut butter.
So you just hold it in one place and squirt 25 times?
Right, you would have to squirt 25 times, which in the end isn't really getting you anything. But the point is, this idea of the peanut butter gun is how the universe works. whenever you have a point source radiating stuff from a point, if you double the distance away, you get 1/4 the intensity. If you triple the distance away, you get 1/9 the intensity, and so on, according to 1/d squared. This always works this way. All right? It works this way whether you're talking about peanut butter, whether you're talking about water, whether you're talking about light, whether you're talking about sound, whether you're talking about gravitational field from a planet, GMM over d squared, right? Whether you're talking about electric field, KQQ over d squared. Any kind of field that's radiating from a point source goes off according to 1/d squared. And we're going to continue this idea tomorrow.